Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
An international team of scientists led by Lucile Turc, an Academy Research Fellow at the University of Helsinki and supported by the International Space Science Institute in Bern, has studied the propagation of electromagnetic waves in near-Earth space for 3 years. The team has studied the waves in the area where the solar wind collides with Earth's magnetic field called foreshock region, and how the waves are transmitted to the other side of the shock. The results of the study are now published in Nature Physics. How the waves would survive passing through the shock has remained a mystery since the waves were first discovered in the 1970s. No evidence of those waves has ever been found on the other side of the shock, says Turc. The team has used a cutting-edge computer model, Lucile Turc, developed at the University of Helsinki by a group led by Professor Minna Palmroth, to recreate and understand the physical processes at play in the wave transmission. A careful analysis of the simulation revealed the presence of waves on the other side of the shock, with almost identical properties as in the foreshock. Once it was known what and where to look for, clear signatures of the waves were found in satellite data, confirming the numerical results, says Lucile Turc. The waves in the foreshock can enter the Earth's magnetic field around our planet as a magnetic bubble, the magnetosphere, which shields us from the solar wind, a stream of charged particles coming from the Sun. Electromagnetic waves, appearing as small oscillations of the Earth's magnetic field, are frequently recorded by scientific observatories in space and on the ground. These waves can be caused by the impact of the changing solar wind or come from the outside of the magnetosphere. The electromagnetic waves play an important role in creating adverse space weather around our planet. They can, for example, accelerate particles to high energies, which can then damage spacecraft electronics, and cause these particles to fall into the atmosphere. On the side of Earth facing the Sun, scientific observatories frequently record oscillations at the same period as those waves that form ahead of the Earth's magnetosphere, singing a clear magnetic song in a region of space called the foreshock. This has led space scientists to think that there is a connection between the two, and that the waves in the foreshock can enter the Earth's magnetosphere and travel all the way to the Earth's surface. However, one major obstacle lies in their way. The waves must cross the shock before reaching the magnetosphere. At first, we thought that the initial theory proposed in the 1970s was correct. The waves could cross the shock unchanged. But there was an inconsistency in the wave properties that this theory could not reconcile, so we investigated further, says Turc. Eventually, it became clear that things were much more complicated than it seemed. The waves we saw behind the shock were not the same as those in the foreshock, but new waves created at the shock by the periodic impact of foreshock waves. When the solar wind flows through the shock, it is compressed and heated. The shock strength determines how much compression and heating take place. Turc and her colleagues showed that foreshock waves are able to tune the shock, making it alternatively stronger or weaker when wave troughs or crests arrive at the shock. As a result, the solar wind behind the shock changes periodically and creates new waves, in concert with the foreshock waves. The numerical model also pinpointed that these waves could only be detected in a narrow region behind the shock, and that they could easily be hidden by the turbulence in this region. This likely explains why they had not been observed before. While the waves originating from the foreshock only play a limited role in space weather at Earth, they are of great importance to understand the fundamental physics of our universe. Make a difference. Sponsored opportunity story source. Materials provided by University of Helsinki. Original written by Johanna Polinen. Note: content may be edited for style and length. Journal reference: L. Turc, O. W. Roberts, D. Verscharen, A. P. Dimmick, P. Keidak, M. Palmrath, Y. Phou Kempf, A. Jolander, M. Dubert, E. K. J. Kilpua, J. Sosik, K. Takahashi, N. Takahashi, M. Batterby, U. Gantz. Transmission of foreshock waves through Earth's bow shock. Nature Physics, 2022, doi 10.1038, S41567, 022, 01837Z. Cite this page. University of Helsinki. New study models the transmission of foreshock waves towards Earth. Science Daily. Science Daily, the 22nd of December 2022. ift.tt/K5 Rugel. University of Helsinki. 2022, December 22. New study models the transmission of foreshock waves towards Earth. Science Daily. Retrieved December 22, 2022 from ift.tt/K5 Rugel. University of Helsinki. New study models the transmission of foreshock waves towards Earth. Science Daily. ift.tt/K5 Rugel. Accessed December 22, 2022. Thanks for watching. Please subscribe my channel for more videos.